So, welcome to module 5.1, and in this module we will be now moving on to the construction of an assembler. We have already used an assembler which was provided by the software, but now we will design our own assembler, and that is very important for us to understand how what we call as the system softwares work. So, with this we actually welcome you to the systems programming part of this course. Whatever we have done so far is the hardware, and now this we need software that can execute on this hardware. So, building a hardware is like building a dam, right, and you have to fill it with good water. The good water is the software. So, software development is very important to have an efficient, effective utilization of your hardware. And what we will be doing in the remaining part of this course is to understand how software is being built for basically execution on the hardware. And the first software that we will see is actually an assembler, which will take a machine instruction and in a mnemonic form and convert it into a 16-bit hack instruction. Right. We have already used an assembler. For example, if you have D equal to M plus D or M plus A, we know how to get that 16-bit instruction for this, for a jump. All these things we have seen in the past, right. But now we need to write a software which will convert that D equal to M plus A into that 16-bit string, and that is essentially what the assembler will do. Now, in the initial portion of this course, we did mention that there is a machine instruction, then there are some programming languages, and there is a compiler which will convert your programming language constructs onto the machine language, and that software is what we call as a compiler. The compiler is a software that will take an high level language and basically convert it onto a machine language. Now, this conversion is not going to be that straightforward. To actually make this conversion process more effective, more simpler, all the recent software stacks, we call it as a software stack. What is a stack? Stack is nothing but a layer in which there are items one on top of another. So, a stack of numbers would have say 5, 6, 7 sitting on top of 6, etc. A software stack is nothing but a layer, a collection of softwares, one sitting on top of another. Now, this is a software stack because assembler is the bottom, which directly talks to the hardware, right, and on top of it we have what we call as an interpreter, and then we have a compiler. Each of them is a software, one sitting on top of another. So, we call it as a software stack. Okay. Now, taking a high level language, the language that we will be introducing in this course, we can't write a compiler for an entire C language, right, it is a part of a small course like this, but nevertheless we need to understand how compilers work, and that is also one of the most important objective of this course. So, we have taken an abridged version of Java called Jack, right, as you can see in the book, the prescribed reference book. I hope you have purchased the book or e-copy, so it is very important for you to have that so that you can follow this course, okay, right. So, we have a Jack, right, Jack is the language, and we have a compiler for Jack. So, what will that compiler do? As per our initial understanding, the compiler need to take a program written in Jack and convert it into the machine language or the mnemonics, right. So, and that mnemonic will in turn be converted into binary by the assembler that we are writing now, and that binary will run on the hardware. But that translation from Jack directly to the mnemonics is going to be very not that straightforward. So, to make that process simpler, we introduce a machine which is called a machine which is a soft machine. So, that is what we call it as a virtual machine, right. So, we introduce a virtual machine what we call as a stack based virtual machine, right. What is a virtual machine? It is actually not a physical hardware, but it is a soft model of that hardware, right. So, so that virtual machine will have a machine, it will have its own instructions. The virtual machine also will have its own instructions. So, what happens here? Your compiler will take that Jack program and translate it into the instructions of the virtual machine, right. So, this is the role of your compiler. So, you write a program in Jack, your compiler will take that program and convert it, translate it into instructions of your virtual machine. Now, what will now we will write an interpreter that will translate these instructions of this virtual machine into your mnemonics of hack. Mnemonics are what we have seen, no, at the end d equal to d plus m, all those programs that we have seen so far. So, that will be the mnemonics of hack. This mnemonics of hack will in turn be taken by the assembler that you are writing now, and that will create you the machine instructions, the 16-bit machine instructions which are in binary, and that 16-bit machine instruction will essentially be executed on the hack, right. Now, we have created an hardware which can accept these 16-bit machine instructions, binary machine instructions, and run it. Now we have to build this entire assembler, interpreter and compiler in the remaining part of this course. So, and to just sum up this, ultimately the user can write a program in Jack, use the compiler that you have made to convert it into an instruction. The entire Jack program will be converted into instructions of the virtual machine. We will be introducing the virtual machine, its instruction set, and this compiler will compile it to that, and then the instructions of this virtual machine will essentially get converted into the mnemonics of hack by the interpreter that you will be writing, and then that mnemonics of hack will then be converted into a 16-bit machine instruction by the assembler that you are writing. So, essentially we have three software, one sitting on top of another. So, compiler is the first from the top point, compiler is the first, then its output is interpreted by the interpreter and its output is assembled by the assembler. So, essentially this is the system programming stack. What we want to give you as a takeaway from this course is an experience to write these software and understand the complexities. There are a lot of simple things that you will learn which in the long run will make you understand the compiler for C and what they call as LLVM. The virtual machine, there is a low level virtual machine LLVM. For you to actually appreciate how LLVM works, an understanding of the VM here will be very useful for you to appreciate how LLVM works. And then from there the interpreter to the mnemonics, and of course the assembler which will take this mnemonics and convert it to 16-bit. So, this is the exercise. So, the way we will be writing the software is first we will write the assembler, then we will write the interpreter, then we will write the compiler. So, we will go in this bottom up fashion for that, right, and that is what you will be seeing in the remaining modules of this course. Now, let us look at the assembler. As I mentioned, the assembler will take the mnemonics of hack and it will convert it into 16-bit hack binary codes, okay, and we will understand this procedure of conversion from mnemonics to 16-bit hack binary code. We will understand the conversion and then we will code it. So, you can start coding it in C++ or C or C# or Python or whatever language you know. I basically assume that everyone knows C because every curriculum across the country has C as an introductory language. So, My orientation for this, of course, so I will give you a generic template of how to develop the software, right, and you can use any of the languages to actually implement the template, and I will be showcasing a C based implementation, but from the template you can translate it into C++ or Java or Python or anything of that, anything of your choice, whatever you are comfortable, right. But the ultimate goal is to take the mnemonics and give you a 16-bit hack. But more importantly, we should also understand how the assembler works, right, and that is very important from understanding the systems engineering, right. So, first we will describe how the assembler works, then we will go ahead and tell what is the generic template for basically developing a assembler, the software, how to write the software, right. Right. So, now to just have a quick understanding, the instructions are there in the instruction memory, the data is there in the data memory, right. So, when you assemble, you assume in the context of hack that all your instructions will be in the put finally into the instruction memory, and all your data will be that instructions use will be in the data memory. Both the instruction and data memory start with address 0. So, if I say address 0, we need to tell whether it is address 0 of the instruction memory or address 0 of the data memory, right. So, there are two different memories, and of course, the data memory comprises of your RAM 16K plus your screen and also your keyboard, as we had described in the previous module, right. So, this is the understanding. So, when we write an assembler, we need to have, first thing that we need to know is the memory model. The memory model here is that instructions are separate, they start from 0 and go, and then the data is separate and again it starts from 0, and we could have up to 16K of data, and of course, after that we have 8K of screen, and then we have 1 word of keyboard, right. So, this is how the whole thing is organized. With this as a framework, let us quickly go and see what is the role of the assembler. Let me just revise, it is already a week now. So, let me quickly revise. What is the output of the assembler? So, the input, so assembler takes an instruction and converts it into the binary. Now, there are two types of instructions that we have seen already. One is the A instruction, another is the C instruction. I will quickly revise what the A instruction is. It is again 16 bits, both the instructions are 16 bits. The most significant bit that you see here, distinguishes whether it is an A instruction or a C instruction. If the most significant bit is 0, then it is an A instruction. If the 3 most significant bits are 1, 1, 1, then it is a C instruction. Now, what will the A instruction do? What is the format of the A instruction? Then there will be a value which is a 15-bit value, right. So, if I and from the mnemonic point, it is of this type at value. So, when I say at value, immediately this will be translated to having one bit as 0, the first bit as 0, and the value that you have, value is a non-negative decimal number, or it can also be a symbol. That 15 bit of that value should be put here following the 0, and that will be the 16-bit binary of this A instruction. The C instruction is of the form destination is equal to computation semicolon jump. So, either I will have computation semicolon jump, or I could have destination is equal to some computation. So, I will have two types of C instruction here, comp semicolon jump or destination is equal to comp. Okay. So, right, and the binary is of this form, the first 3 bits are 1 1 1, this A bit as such and the 6 bits basically are the computation. The A bit will tell where the source operand is and C1 to C6 will tell what we need to do with the source operand. We have already seen that in detail. The destination, if at all it exists, in the case of jump this destination will not exist. In the case of non-jump, if the destination exists, then the D1, D2, D3 bits as you see here will tell you what is the destination, and if it is of this type, the jump type, then this J1, J2, J3 will tell you what is the type of jump. So, if I have an instruction dest is equal to comp, automatically the J1, J2, J3 becomes 0. The dest will tell me what is D1, D2, D3, the comp will tell me what is A, C1, C2 to C6. If I have comp semicolon jump, then this D1, D2, D3 are 0, then of course the comp will tell me what is A and C1 to C6 and the jump will tell me what is J1 to J2, J1, J2 and J3, right. And we said that it will tell what will dest tell. So, this is how it is. These tables are very clear. If your destination is, if your comp is 0, then I have to put A equal to 0 and 1 0 1 0 1 0. If your comp is 1, then I should put A equal to 0 and 1 1 1 1. If your comp is minus 1, then I have to put A equal to 0 and this. If your comp is D, I have to do this. If your comp is A, I have to do this. If your comp is not D, I have to do this. Not A, minus D, minus A, D plus 1, A plus 1, full. If your comp is M, then I have to pay A equal to 1 and 1 1 0 0 0. Not M minus M, M plus 1, M minus 1, D plus M, D minus M, M minus D, D and M, D are M, etc. So, by parsing that comp, what do you mean by parsing? By actually reading that comp part alone of that instruction, we can go and finalize what is A and what is C1 to C6, which are these bits of your C instruction, right. Now, the challenges are, if I want to write a very robust assembler, I may write M minus 1, I can also write it as minus 1 plus M, I can write D plus M, I can write M plus D, I can write minus M plus D, right, minus D plus M, right, I can write M minus D, I can write. So, all these things are possible, right. So, these are all some of the possible combinations of, right, and similarly D minus A minus D, D and A. So, sorry. So many things are actually possible here. So that is the challenge in actually writing an assembler, right. The way the mnemonics are generated can be in different form, right. We can't just say I want M minus 1. I could have also actually have even minus 1 plus M, right. I need not have D plus A, I could have A plus D also, and these things have to be basically catered to when you write the assembler. So, these are challenges in writing the assembler, and these challenges you will realize only if you write an assembler on your own, and you may not get an opportunity or you may not get time enough in your curriculum to write an assembler for a large C language, right. So, or for an instruction set as complex as say Intel or ARM. So, this is an opportunity. So, what this course essentially does is giving you an opportunity to write an assembler and understand all those small intricacies on a very small elegant machine. So, that is the important thing, and that is the importance of this exercise also, right. So, now we understood how we fill up this A to C6. We have already done that. I am just revising it so that it becomes, I reinforce some of the concepts that we have done earlier. And this is about the D1, D2, D3. And when do we fill this D1, D2, D3? When your destination exists. In the case of jump, destination does not exist. When your destination exists, we fill it up. Right. And this is how. So if I have just A, I have 0, 0. If I have D, I could have, if I have M, then this is, but I could have A and D, I could have MAD, I could have DAM. So I could have MAD, DAM, DMA, right? Right. Similarly, MD, DM, MA, AM, AD, DA. So all these possible combinations I could have here. Right. And similarly for the jump is very straightforward. So if I have null, then I have to put 0. If I have JGT, JEQ, JEG, these are all the mnemonics, and based on that I can basically fill up this J1, J2, J3 part of this stuff, right. So these three tables are extremely important for us to understand how do we fill, how do we, from the mnemonic, how do we actually get to this 16-bit binary, right. So we will be using these three tables extensively for our as a part of this assembler development. Okay. Now, so this is the machine model. We have already seen this machine model. So the instructions are going to be in this ROM 32K. So we have 32 kilo words of instructions. So 32K instructions I can put. What is 32K? 2 power 10 into 2 power 5. So 2 power 15 instructions I can put. Similarly, your data memory has 16K of, that is 2 power 14 words of data you could have. Every data is 16 bits in this machine, and of course 8K of screen and 1 word of keyboard. So this is the memory model, and so always my instructions will start with 0 and always my data also will start with 0, and this is how we build the assembler. So this is a basic assumption that we have when we want to build the assembler. So now we will go to the next module, where we will be describing what are the challenges in building that assembler. So some of the small nitty-gritties of building the assembler, and we will conclude that module. At least before we end that module, we will see what is the 2-pass assembler. Okay. Thank you.